Hello everyone. Today we are going to analyze this beam using stiffness matrix method. Before analyzing, let's see the beam one time. In this beam, we are having two spans, span AB and span BC. In the span AB, we are having a point load acting on the center. In the span BC, we are having uniformly distributed load acting for the full span. Span AB is 10 meter long, span BC is 8 meter long. There are three supports in this beam, in the point A, in the point B, and in the point C. There are supports. All the supports are roller supports. In the point A and in the point C, we are having roller supported ends. In the roller supported end, there will be no movement, only there will be the vertical reactions. So in the point A, MAB will be 0 and in the point C, MCB will be 0. In the joints, there will be two movements. In the joint B, we are having two movements. One movement will be acting in the clockwise direction and another will be in the anti-clockwise direction. But both of the movements will be having the same value. So in this analysis, we have to find two movements and three reactions RA, RB and RC. Now let us make the fixed end moments. For making the fixed end moments, we have to assume every span as a separate fixed beam. First, let us make the fixed end moments in the span AB. You can see that I have assumed the span AB as a separate fixed beam. In this table, you can see some of the important fixed end moments for the different type of loadings. In the span AB, we are having point load acting on the center, so we have to select this condition. The formula for the fixed end moments are minus WL upon 8 and positive WL upon 8. In the span BC, we are having UDL acting for the full span. So we have to select this condition. The formula for the fixed end moments are minus WL square upon 12 and positive WL square upon 12. In the span AB, we are having a point load acting on the center. We just saw the fixed end moment formulas minus WL upon 8 and positive WL upon 8. M of AB is negative because it is acting in the anticlockwise direction. M of BA is positive because it is acting in the clockwise direction. Let us apply the values in the formula. W is 72, L is 10. After applying, we are getting M of AB is equal to minus 90 kN meter and M of BA is equal to 90 kN meter. Now let us make the fixed end moments in the span BC. In the span BC, we are having UDL acting for the full span. We already saw the formula for the fixed end moments. Minus WL square upon 12 and WL square upon 12. Let us apply the values inside the formula. W is 36 and L is 8. After applying, we are getting M of BC is equal to minus 192 kN meter. M of CB is equal to 192 kN meter. In the stiffness matrix method, we have to check the number of supports in which slope can occur. Let us see the conditions. In the fixed support, there will be no slope. In the hinged support, there will be slope. And in the roller support also, there will be slope. In this beam, we are having three roller supports. In the point A, in the point B, and in the point C, we are having roller supports. So the number of supports where slope occurs is 3. In the point A, we are having theta A. In the point B, we are having theta B. And in the point C, we are having theta C. So in this analysis, we are having 3 unknowns. If we calculate these 3 unknowns, we can easily find the final moments. Now let us make the fully restrained structure. In the fully restrained structure, there will be no slope. We know that only in the fixed supports there will be no slope. So let us remove the roller supports from the point A, B and C and replace them with the fixed supports. In this beam, there will be no slope because all the supports are fixed. That is why it is called fully restrained structure. We have made the fully restrained structure. Now let us make the coordinate diagram. In this analysis, we are having 3 coordinates. In the point A, in the point B, and in the point C, we are having the coordinates. Because in these points we had slope and we replaced the roller supports with fixed supports. So the coordinates are 3. In the points A, B and C we are having the coordinates. The coordinates should be made in the clockwise direction. You can see that all of the coordinates are in the clockwise direction. Now let's see the formula to calculate the slope values. System displacement delta matrix is equal to K matrix inverse into P matrix minus PL matrix, where PL matrix is equal to moments developed in the coordinates due to the given load. P matrix is equal to final forces acting in the coordinate direction. K matrix is equal to stiffness matrix. In this formula, first let us find PL matrix. We know that PL matrix is the moments developed in the coordinates due to the given load. In the beginning, we have calculated the fixed end moments due to the loads. So for the PL matrix, we have to apply the fixed end moments. But we must be very careful. We have to enter the moments in the order, first for the first coordinate, then for the second coordinate, finally for the third coordinate. The first coordinate is the point A. In the point A, we have calculated one fixed end moment, that is M of AB. We can apply the value. In the point B, we have calculated two fixed end moments, M of BA and M of BC. We have to add them. After adding, we are getting minus 102. In the point C, we have calculated one fixed end moment, that is M of CB. Let us apply the value. In this way, we can easily make PL matrix. The size of the PL matrix will be according to the number of coordinates. Here we are having 3 coordinates. So here we are having 3 values. Now let us calculate the P matrix. If in the beam there is overhanging, there will be value in the P matrix. Otherwise, we can simply enter 0, 0, 0 for the 3 coordinates. Since we are having 3 coordinates, there will be 3 values for P matrix. All the values are 0 since we are not having any overhanging in the given beam. In this formula, we have calculated the PL matrix and P matrix. Only one is remaining, that is the stiffness matrix. Let us find that. Now let's see how to calculate the stiffness values. For calculating the stiffness values, we have to apply unit displacement, that is theta is equal to 1 radian in every coordinate. In this analysis, we are having 3 coordinates. In the point A, in the point B and in the point C, we are having the coordinates. So we have to apply the unit displacement in these coordinates. Then we have to use the formulas. If the fare is fixed, the formula is 4EI upon L. If the fare end is hinged, the formula is 2EI upon L. Here we have to be careful. We should not apply the unit displacement in the given beam. We have to apply the unit displacement in the restrained structure. Now let's see the size of the stiffness matrix. For 3 coordinates, the size will be 3 by 3. For 2 coordinates, the size will be 2 by 2. For 1 coordinate, the size will be 1 by 1. In this analysis, we are having 3 coordinates. So the size will be 3 by 3. In the matrix, we will have 3 rows and 3 columns. First, let us find the first row. For that, we have to apply the unit displacement in the first coordinate. Let us apply the unit displacement in the point A. In the point A, we are having a fixed support, but when we apply the unit displacement, it is no longer a fixed support, it becomes a hinged support. Because in the fixed support, there will be no displacement, but we are applying unit displacement. When we apply the unit displacement, the fixed support becomes a hinged support. Here we have to find 3 stiffness values K11, K12 and K13. All the coordinates should be made in the clockwise direction. You can see that all of the 3 coordinates are in the clockwise direction. Now let's see how to draw the slope curve. We are applying unit displacement in the point A. So in the point A, we have to make a clockwise curve towards the point B. Then we have to see the direction of the arrow. This arrow is indicating downwards. So we have to make the curve below the span. We have to be very careful. The curve must end before the fixed support, because in the fixed support there will be no slope. You can see that I have given some gap here. That is why the slope curve ends before the point B and can't continue after the point B. Now let us find the stiffness values. The stiffness values should be calculated in the order. First for the first coordinate, then for the second coordinate, finally for the third coordinate. Let us calculate K11. For that, from the point A, we have to look on both the sides. On the left side, there is nothing. On the right side, we are having a fixed support. If the Faraday is fixed, the formula is 4EI upon L. The length of AB is equal to 10 meter. We can apply. Finally, we are getting 0.4 EI. Now let us calculate K12. K12 is located in the second coordinate B. So from the point B, we have to look on both the sides. On the right side, there is no slope curve. If there is no slope curve, there will be no stiffness value. On the left side, we are having a hinged support. If the Faraday is hinged, the formula for stiffness is 2EI upon L. The length of AB is 10 meter. We can apply. Finally, we are getting 0.2 EI. Now, let us find K13. For that, from the point C, we have to look on both the sides. On the right side, there is nothing. On the left side, there is no slope curve. In this case, there will be no stiffness value. So, K13 is equal to 0. Now let us make the second row in the stiffness matrix. For that we have to apply the unit displacement in the second coordinate, that is the point B. In the point B we are having a fixed support, but when we apply the unit displacement, it is no longer a fixed support, it becomes a hinged support. The coordinates should be made in the clockwise direction. You can see that all of the coordinates are made in the clockwise direction. Now let us see how to make this slope curve. We are applying unit displacement in the point B. The point B is a joint. It is connecting two spans. So we have to make two curves, one towards the point A and one towards the point C. You can see that I have made two curves. Both of the curves are made in the clockwise direction. The first curve towards the point A and the second curve towards the point C. Now we have to see the direction of the arrows. This arrow indicates upwards, so the curve comes above the span. This arrow indicates downwards, so the slope curve comes below the span. Also, we should be very careful when we make the curves. Some gap should be given between the curves and the fixed supports, because in the fixed supports there will be no slope. Now let us calculate the stiffness values. To calculate K21, from the point A, we have to look on both the sides. On the left side there is nothing. On the right side we are having a hinged support. If the parent is hinged, the formula is 2EI upon L. The length of AB is equal to 10 meter. Finally, we are getting 0.2 EI. Now, let us calculate K22. For that, from the point B, we have to look on both the sides. On the left side, we are having a fixed support. If the parent is fixed, the formula is 4EI upon L. The length of AB is 10 meter, we can apply. On the right side also, we are having a fixed support. So, we have to apply the same formula, 4EI upon L. The length of BC is equal to 8 meter, we can apply. After adding these two values, we are getting 0.9 EI. Now, let us calculate K23. For that, from the point C, we have to look on both the sides. On the right side, there is nothing. On the left side, we are having a hinged support. If the parent is hinged, the formula is 2EI upon L. The length of BC is 8 meter. We can apply. Finally, we are getting 0.25 EI. Now, let us make the third row in the stiffness matrix. For that, we have to apply the unit displacement in the third coordinate, that is the point C. In the point C, we are having a fixed support, but when we apply the unit displacement, it is no longer a fixed support, it becomes a hinged support. Now, let's see how to make this curve. We are applying unit displacement in the point C. So, from the point C, we have to make a clockwise curve towards the point B. Then we have to see the direction of the arrow. This arrow is indicating upwards. So the slope curve comes above the span. In the fixed support there will be no slope. So we have to give some gap between the fixed support and the slope curve. That is why the slope curve ends before the point B and can't continue after the point B. Now let us find the stiffness values. To calculate K31, from the point A, we have to look on both the sides. On the left side there is nothing. On the right side there is no slope curve. In this case, there will be no stiffness value. So K31 is equal to 0. Now let us calculate K32. For that, from the point B, we have to look on both the sides. On the left side there is no slope curve, so no stiffness value. On the right side we are having a hinged support. If the parent is hinged, the formula is 2EI upon L. The length of BC is 8 meter, we can apply. Finally we are getting 0.25 EI. Now let us calculate K33. For that, from the point C, we have to look on both the sides. On the right side, there is nothing. On the left side, we are having a fixed support. If the Faraday is fixed, the formula is 4EI upon L. The length of BC is 8 meter. We can apply. Finally, we are getting 0.5 EI. In the stiffness matrix, we have calculated all of the rows. We can enter them. EI is common for all of the values, so we can take it outside. In the system displacement formula, we have found the stiffness matrix, the P matrix and the PL matrix. Let us apply all the values. We can take EI outside. We know that EI inverse is equal to 1 by EI. For this matrix, we have to find the inverse. We can apply all of the values in the calculator and get the inverse. If you do not know how to find the inverse of a 3 by 3 matrix in the calculator, see the description below. There is a link. You can click the link and watch the video for getting ideas how to find the inverse of a 3 by 3 matrix in the calculator. I have used the calculator and found the inverse. We can add these two matrices. After adding, we are getting these. Then we have to multiply these two matrices. We have to multiply all the rows with the column. You can see the multiplication here. Finally, we are getting the answers. We know that in this problem, the system displacements or the slopes, which we found finally. The slope values will be according to the coordinates. The first coordinate is the point A. So first we will get theta A. The second coordinate is the point B. So here we will get theta B. The last coordinate is the point C. So here we will get theta C. In this problem, we have found the unknowns. Now we can make the slope deflection equations and apply these values and find the final moments. In the point A and in the point C, there will be no moment because they are the simply supported ends. So MAB is equal to 0 and MCB is equal to 0. For them, there is no need to make the slope deflection equations and waste the time. Only make the slope deflection equations for MBA and MBC. In the beginning, we have already calculated the fixed end moments. We can apply them. Length of AB is 10 meter and length of BC is 8 meter. When we apply the values of theta A and theta B, we are getting MBA. When we apply the values of theta B and theta C, we are getting MBC. In this beam, we have calculated the final moments. For MBA, we are getting a positive value. That means it is acting in the clockwise direction. For MBC, we are getting a negative value. That means it is acting in the anticlockwise direction. Now, let us calculate the reactions. First, let us take the span AB and calculate the reactions. In the span AB, we are having a movement MBA which is acting in the clockwise direction. So, when we calculate the reactions in the span AB, we have to take the moment MBA. In this span, first I am going to calculate the reaction RA. For that, I am going to take moment about B. In this case, I am moving towards right hand side. Clockwise will be positive and anticlockwise will be negative. The reaction RA is acting towards the point B in the clockwise direction. So it will be positive and the distance is 10 meter. So 10 RA. The point load is acting towards the point B in the anticlockwise direction, so it will be negative and the distance is 5 meter. So minus 72 into 5. The moment is acting in the clockwise direction, so it will be positive. Finally, we are getting RA is equal to 15.7 kilonewton. To find out RB1, let us apply the rule. Summation of vertical forces is equal to 0. We are having three vertical forces, RA and RB1 are acting upwards, so they will be positive. The point load 72 kN is acting downwards, so it will be negative. RA we have already calculated, we can apply that. After calculation, we are getting RB1 is equal to 56.3 kN. Now let us take the span BC and find out the reactions. In the span BC, we are having an anticlockwise movement MBC which is equal to 203. In this span, first I am going to calculate RB2. For that I am going to take movement about C. In this case also, I am moving towards right hand side. Clockwise will be positive, anti-clockwise will be negative. RB2 is acting towards the point C in the clockwise direction, so it will be positive and the distance is 8 meter, so 8 RB2. The UDL is acting towards the point C in the anti-clockwise direction, so it will be negative and the distance is 8 meter. When the UDL comes, we have to multiply with the distance and the distance by 2, so 8 by 2. The movement is acting in the anti-clockwise direction, so it will be negative. Finally, we are getting RB2 is equal to 169.375 kN. Now let us apply the rule summation of vertical forces is equal to 0. Here we are having three vertical forces, RB2 and RC are acting upwards, so they will be positive. The UDL is acting downwards, so it will be negative. When the UDL comes, we have to multiply with the distance to get the total load. Finally, we are getting RC. We have calculated the reaction in the point B 2 times, so let us add them. Finally, we are getting RB. Now we are going to draw the shear force diagram. Before drawing shear force diagram, let us calculate the shear force values. I am calculating the shear force values from the point A to the point C. In this case, I am moving towards right hand side. The upward forces will be positive. The downward forces will be negative. You can see the calculations here. For the point loads, we have to calculate the shear force at just left of the point and just right of the point. Now you can see the shear force diagram. If there is UDL, the shear force line will be inclined. You can see that in the span BC we are having UDL, that is why we are getting inclined line. For the point loads, it will be a straight line. In the shear force diagram, if you are getting negative values, we have to draw below this line. If you are getting positive values, we have to draw above the line and then mark positive and negative. Now let us make the bending moment diagram. For that, first we have to make the free movement diagram, then end moment diagram. After, we have to combine both of them to get the bending moment diagram. For making the free movement diagram, we have to consider each span as a separate simply supported beam and then draw the bending moment diagrams. In a simply supported beam, if the point load is acting on the center, the formula for maximum bending moment on the center is WL upon 4. Here W is 72, L is 10. We can apply in the formula, finally getting 180 kN meter. In the simply supported beam, if the UDL is acting for the full span, the formula for bending moment is WL square upon 8. Here W is 36, L is 8. We can apply in the formula, finally getting 288 kN meter. We know that if your point load is acting in the simply supported beam, the bending moment diagram will be in the shape of a triangle. If the UDL is acting, the bending moment diagram will be in the shape of a parabola. In most of the cases, the free movement diagram will be positive. It will be rarely negative when there is coupled movement in the beam. Now let us draw the end moment diagram. We have already calculated the final moments. Using these moments, we have to draw the end moment diagram. In the point A and in the point C, the moments are 0. So the end moment diagram will be 0 in the points A and C. In the point B, we are having two moments, MBA and MBC. MBA is acting in the clockwise direction and MBC is acting in the anti-clockwise direction. For drawing the bending moment diagram, we have to see the direction of the arrows. Both of the arrows are indicating upwards. That means we have to fix this point above this line. Then we can join this point from the point A and from the point C. We already know in the point A and in the point C, the bending moment is 0. Even though we are having two movements here, we should not make 2 points. Only one point we must make because both of these arrows are indicating upwards. End moment diagram will be negative if it comes above this line. If it goes below the line, that will be positive. Right now it comes above the line, that is why it is negative. We have made the free movement diagram and end moment diagram. Now let us combine both of them and draw the bending moment diagram. After combining, wherever they are acting alone without mingling, we have to mark them. Here we are having the free movement diagram alone, so we are marking as positive. Here end moment diagram, so negative. Here free movement diagram, so positive. Then we have to mark the values also. Wherever the free movement diagram and the end moment diagram are acting together, we are not marking anything, we just keep the space empty. If you are very experienced, no need to draw free movement diagram and end moment diagram. You can directly draw the bending moment diagram and save a lot of time. Now we are going to end this session. Thank you for watching this video.